Hello, everyone, and welcome. I'm Jennifer Callahan from ICCT's communications team. Thank you for attending this webinar. Today, we're going to talk about the air quality and health impacts of large-scale vehicle electrification in India. The presenters are Arijit Sen of ICCT and Pavan Kumar Nagar of IIT Kanpur. Arijit is an associate researcher at the ICCT and the lead author of the briefing paper upon which today's presentation is based. He has a PhD in public policy from the University of Maryland, College Park. At ICCT, his work focuses on upgrading global and national transportation models and conducting applied research that leverages those models. Pavan has a PhD in environmental engineering technology from IIT Kanpur, and he's a postdoctoral researcher in the school's Department of Civil Engineering. A few housekeeping items before we begin. This webinar is being recorded. All the slides will be posted to the ICCT website on the event page for this webinar. That'll be shortly after. The recording will also be available on that page in a couple of weeks, and it'll also be on our YouTube channel. Your microphones are on mute. If you have questions during the presentation or afterward, please write them in the questions box. That box is in the control panel to the right of your screen. After the presentation, we'll have a few minutes to answer some questions. Arijit, please go ahead.
Thanks, Jen. Welcome, everyone. So just to give you an idea about what we're going to talk about, so we're going to delve into the background of the study a bit and establish the research questions. Then we'll get into scenario design and how we exactly model things. Then we will discuss the things that we have modeled and the results. And finally, as you can see, we have modeled 3 different things that has their own results, and the conclusions section will tie them all together. All right. So we know that India has relatively poor air quality, and that has a lot to do with local pollutant emissions, and specifically those emissions from transportation and the power sector. So now we ask you the questions that if India embarks on an ambitious vehicle electrification policy, does that improve air quality? And additionally, if there is power sector policies that links of the grid, how does that help vehicle electrification in terms of boosting the air quality? So we are looking at 5 different scenarios, and this is mostly due to changes in the differences in power sector measures and vehicle electrification measures. Now, for baseline scenario, we have business as usual for EV sales, which is about 1% of all the new sales, and that's relatively flat. For power sector, it's a relatively high share of fossil fuel generation in the grid. And if we look at emission controls at the bottom, we have generally high level of emissions due to lower control efficiency. Then we go to a reference scenario, which adds an ambitious EV scenario, which is about 95% of the total of total vehicle sales is EV by 2040. The improved emissions control scenario keeps that ambitious EV, but adds improved emission controls in the power sector, which means that more stringent NOx and SO2 controls. The coal phase out scenario keeps the ambitious EV scenario for vehicles, but it also drastically cuts down the share of coal in the generation mix. And then finally, we have the combined scenario, which keeps in the ambitious EV scenario, but it combines the improved emission controls and the coal phase out. So this is basically our strongest scenario when it comes to emission reductions from the vehicle sector and the power sector. So we use like 3 different models to get to our results, and this is a flowchart explaining that. So we model our road transport emissions using ICCT's in-house IEM model. We took the help of IIT Kanpur in modeling the power sector emissions. The other emissions were obtained from Eclipse. Then we got to grid emissions for all the sectors. These grid emissions were then fed into the WRF-Chem air quality model, which Pawan will talk about later in greater detail. And using the air quality model, we got ambient concentrations for different scenarios. These concentrations were then fed into ICCT's fate modeling tool, which calculates health impacts both in terms of avoided premature deaths and the financial valuation of that. So we start from emissions, we end up at health impacts, and we model the air quality impacts in between. So yes, I'm not going to spend too much time on this slide, but as I said, we use IEM to model the transportation emissions. The power sector emissions were modeled using plant level data by IIT Kanpur. And the important thing here is that whenever there is additional vehicle electrification beyond the baseline, that creates additional generation requirement in the grid, and we're assuming that that is being entirely met through fossil fuel power plants. Whereas in real life, this might not be the case, but we made this assumption in order to be conservative in our results. And here is what our results look like. So as we can see that if we look at overall results, there is a slight increase in primary PM 2.5 in 2030 and SO2 in 2030 as well in the REF scenario. That's a scenario with ambitious EV, but no additional power sector measures. But once those additional power sector measures kick in, you can see that we do see reductions in SO2 and NOx and even PM 2.5. In 2040, with a combination of high electrification and improved power sector emission controls or decarbonization or both, we see that from the baseline, and if you look at the combined emissions of the power sector and the road transport sector, they have mostly declined. Now, this is in itself not very helpful because we don't know how these emissions results affect air quality and especially how it affects air quality at the state level. So in order to see the effects of that, I'm going to hand over the next part of the presentation to Pawan, who is going to explain how we did the air quality modeling and share some of the results.
Thank you, Arjit. So I am going to explain this part. So initially, to model the emissions for using the WRF-Chem model, there initially the national emissions data is especially graded on the 0.5 degree into 0.5 degree. So covering the whole India for the transport and power plant emissions. And other emissions is taken from the eclipse for their current legislation scenarios. Then after the combined data is then used, so metrology is through the all simulation is constant. So the overall impact of change in emission due to the improved emission and implementation of electrical vehicles. So no role of no further variation of the methodology is seen. And after then the concentration is comes, then it is then also converted in based on the population weighted concentrations. Next. Yeah. Next. So this is the overall flow diagram for the execution of the model. So emission from the power sector and the transport and other sectors are combinedly imported on the in net CDF format, which is compatible to WRF-Chem, which is, and the metrology data is taken from the NCP is final operational global analysis data. So after then a combined, so WRF-Chem is executed for the all scenarios like the baseline, reference, improved emission control and coal phase out, and then finally the combined coal phase out and improved scenario. And then the results are temporally and especially analyzed for annual and monthly basis, and as well as the population weighted average concentration of each district and state levels, and then there are summarized. So the graded levels of the concentrations for PM 2.5 and other pollutants is converted at district or state levels using this formula, where the CJ and AJ are the concentrations and area of the respective grid in a particular district or state, divided by the total area of the state or district. Similarly, and population weighted level are of the country is estimated by the concentration of a district or state multiplied by the population of the district or state divided by the total population of the country. So next please. Yeah. So this is the PM 2.5 annual concentration for different scenarios in 2030 and 2040. So there are the red bars showing the baseline concentration, and so in respect of baseline, if we see the air quality is improved by these fractions. So air quality is in final scenarios in COM, it's improved by 2.9 microgram per meter cube. And in 2040, if see the overall improvement in after applying all the control measures and introduction of vehicles, so in final improvement is seen by 4.5 microgram per meter cube at the national level. So these are the distribution of the concentrations in different states. So maximum concentration is observed in baseline is 109 microgram per meter cube and varying in the different parts. So above figure is the for baseline 2030, and with respect of baseline scenario, the other scenario is analyzed, like reference, IC, CP, and COM. So there are the relative changes in the air quality compared to the baseline. So in reference, there are the air quality is looking about the similar as in baseline. Only the few states like the in Gujarat and West Bengal is showing slight improvement. Other states are looking the similar on the similar level as baseline. Also in reference 2040, there are some states in south states and Rajasthan is also showing slight improvement, but other states are about the at same level. So when we came on the IEC, there are the more states are added in the improved air quality, mainly in the east to south, east south states. And in CP also behave like the IEC, and so similar trend is seen. And finally, when we see went in the COM, so there are the many states are falling in the shows the improved air quality, and in COM almost all the states are showing the improved air quality. So after the clear impact of the EVs are seen in finally in 2040, and 2030 is slightly some states are shown as baseline, so there are the less impact. So major impact is in the center part of the country. Yeah. So Arjit, you can take.
Thanks, Pavan. So the last part of the modeling has to do with to take these air quality results that Pavan just described and then to see how that translates to health impacts in terms of avoided premature deaths. So in order to do that, we used our in-house FATE tool. What FATE does is it takes air quality results and then it uses the methods established in GBT 2019 to calculate the number of premature deaths due to certain diseases that are linked to poor air quality. And then once we get that health impact data, we use a value statistical analysis, value statistical life analysis, excuse me, from the World Bank to give a financial quantification of that premature deaths data. So I'm not going to go into too much detail regarding the methods because these are all like long and complicated equations. And if you want to know more about them, you can read the FATE documentation, which is publicly available. But essentially, we calculate the health impacts by using the population fraction that's affected by the outcome and then relative risk curves that are established in the GBT 2019 methods. And then we calculate the value of statistical life by taking the number of avoided deaths and then multiplying that to the World Bank's estimate of one statistical life in the context of India and for different years. So here's the final results that we get to. On the left, we have the avoided premature deaths compared to baseline. So as you can see that all 4 non-baseline scenarios in both the years, that is in 2030 and 2040, there are some avoided premature deaths compared to baseline. Now, that number is relatively low in the REF and the CP scenarios, but it is fairly high in the IC scenarios, and it's the highest in the COM scenario. And now, if you remember the AI quality results, this sort of tracks well with that. And the lesson here is that vehicle electrification on its own will lead to some avoided premature deaths, and this is irrespective of what the power sector is doing. But if you add in all the power sector related benefits of decarbonization and tighter emission controls, we see that the health impact is magnified significantly. And on the right hand side, this sort of translates into the financial terms. You can see the avoided cost of premature deaths. So we start at like 10.3 billion US dollars in terms of 2020 value. And then that goes all the way up to $24 billion in 2030. In 2040, we start with around like $19 billion. And then we go all the way up to about $81 billion. So that sort of helps to put into context the perceived impact of the number of avoided premature deaths. Because if you see the number of premature deaths, they don't seem to be very high, especially given the fact that baseline is probably something like 3 or 4 million, around that range. But then if it's the dollar value, then you do see that, okay, that this is not an insignificant amount of avoided premature deaths at all. So in conclusion, we do see that widespread vehicle electrification will yield net air quality and health benefits, and that is irrespective of what the power sector does. But that being said, if there are additional policies that cleans up the grid, this will significantly amplify the air quality and health impacts results. So this basically means a couple of things. That first, that electrification policies don't necessarily need to wait for the power sector emission control and grid decarbonization policies to catch up. But on the other hand, because of the tremendous benefits that the power sector policies offer, these are policies that should be seriously pursued as well. So rather than hoping for one set of policies coming before another set of policies, the ideal way forward would be to have electrification policies and power sector decarbonization and emission control policies to come up in parallel. Thank you.
Thank you both for that great presentation. Now we have time for the Q&A section. Remember, if you have questions, please write them in the questions box and we'll answer as many as we can. So the first one is about the vehicle electrification assumptions. So the question is, what were your assumptions about the potential for electrification of heavy duty vehicles?
Yes, thanks, Jen. So the 95% sales in 2040, that mainly comes from the fact that if you look at the total vehicle sales in India, it's mostly two and three wheelers and other light duty vehicles. On the heavy duty side, we assume that the trucks are going to be about 50% electrified by 2040, and the buses are going to be electrified by about 65 or 70%.
Great, thank you. So the next one is about the air quality modeling. So Pavan, is there a reason why the improvement for some states, Gujarat being one, reduces between the 2030 and 2040 in that combined scenario?
Yeah. So actually, in improvement in Gujarat and these things, because the wind mostly due to the wind pattern, because the most of time the wind are from northwest, and so and they are near the coastal area, so there are the basically the improvement may be seen in these states, and no more actually traffic transport also less, actually traffic emissions are less in this because the better road infrastructures, and power plants are mostly situated in the east and south regions, so that's why the better air quality is seen in the Gujarat. More improvement.
Great, thank you. So now we have another one about sort of the assumptions. There's been a lot of talk about the success of renewables in India. Most of that is fairly recent. Can you talk some more about your assumptions for renewables in the grid mix under the coal phase out scenario?
Yeah, sure. So another coal phase out scenario, what we have assumed is that that's first of all, in terms of fossil fuels, coal is a dominant fuel. So it's like 80% of all the fossil fuel mix. And so if you take that out, so it's about like 20% or 25% of fossil fuels. Then there's a little bit of nuclear, like 5 to 10%, and then the rest is all renewable. So it's hydro, and most of it's solar, some of it's wind, and a little bit of it's biomass. So I would say that of the renewables mix, which is about 70% of the total grid mix, solar is about 60% of that, and then the rest is hydro, wind, and biomass.
Great, thank you. So sort of here's an interesting kind of counterfactual. How do you, this is a reference to the fact that you assume that the demand from the electric vehicles is going to be powered by fossil fuels. So how do you think the results here, like overall, might have been different if you hadn't assumed that, if it was a just regular percentage of the grid?
Yeah, sure. So if that was the case, then we believe that the electrification results would have been even better in terms of overall emissions, and that would mean that some of the EAQA results would have been marginally better as well. But here's the thing, I mean, in spite of assuming that there's a significant electrification of vehicles, if you look at the overall power sector demand, and let me go back to this. So if you look at the overall emissions just due to this additional demand for electricity due to EVs. And those are these yellow parts, and you can barely see them, right? And which means that in the overall context of power sector emissions, if you sort of add up all the end users, EVs are not a very significant part of it. So yes, so if we assume the regular mix, then this bar probably could be probably even less prominent. But because it's so small now, I don't think the overall results will change that much. I mean, there will be improvements for sure, and probably in the more marginal areas in the map, but the aggregate results probably won't change that much.
Great, thank you. So we're right at about a half an hour now, and I think that's all the questions that we have. So thank you, everyone, for participating in today's presentation. If you do have a question later on, feel free to reach out to the authors. Their email addresses were on that last slide, and again, we'll post the slides on our website. So yeah, thank you so much. Remember to follow us at the ICCT. Thank you again, and we hope to see you soon.
Thank you, everyone.
Yeah, thank you. Bye.